Okay, so in this question, what are they asking us to do? So the question says, determine the forces in each member of the truss and state if the members are in tension or in compression. Then we have this figure that we have to look at. So if we're using the method of joins, we know to say, for the most part, we deal with just the sum of forces. For something in equilibrium, of course, we know to say the sum of forces has to be equal to zero. The sum of the rotations also has to be equal to zero. But if we choose to use the method of joins, then we know to say we're going to focus on just this one. So how will it work? Well, you have to pick one joint at a time. Look at the joint where you will likely only have a few unknowns. So in this case, the joint that is best for us to start with will have to be this joint here. Because when you look at this joint, you have an applied force, which you know, and then you have two members, this member here and this member here. So the two members will represent the unknowns that you have, and the applied force will be the force that you know. So you can easily use the applied force to determine what is happening in those two members. So that is where we're going to start from. So if we look at this member, the first there as in this joint here. So let's say the joint at D. So if we look at the joint at D, what is happening there? Well, for that joint at D, what we're seeing is that if the joint was here, then it means that you have three forces acting on it. So the force, the applied force itself, will be acting vertically downwards, and the value is that 500. So that is the applied force. Then next up, you have the forces in the members. So you have the forces in the members. What is happening to the forces there? Well, for the member DC here, I will say the force, will make an assumption, and the assumption will be that this force is going to the left. So if that is our assumption, that the force is going to the left there, then this is what we're seeing here. So I'll say this is the force. We can label this one DC. Then next, what is happening down here? Well, for this one, you can again make an assumption. You can choose that it is going down, but you should see that the most logical choice here has to be that the member here, yeah, I think down works, down, but down doesn't really sound too good. Especially when you look at the fact that the applied force there is going downwards, you expect that the force along this member will likely have an upward component, so that that upward component gets to oppose that 500, which is being exerted there. So because of that, the assumption I will make for this member is that the force here will be going upwards like that. So I hope you guys saw how I used the system to predict the direction for the force in that member. Okay, so with that in mind, I would choose the force in this member to be going in this direction. So I'll label this as ED. So I'll say this is FED or DE. It doesn't really matter. Okay, so say this is FDE. Okay, so with this done, we now have to resolve this force here, because we see this force is in both the X and in the Y. So we have to resolve this force. The other two are already, they are okay. So how do we resolve this force? Well, we have to see that we're given the distances here. So this 6 feet here represents the vertical distance from there, coming all the way down up to here. While the 3 feet there represents the horizontal distance from the point D to the point E. So what are we seeing here? We are creating a right-angled triangle here, so that, yeah.
I think the 3 feet up to the point F.
Oh, sorry. Yeah, the 3 feet is up to the point F. Yeah, that's okay. I didn't look at it all the way there. Yeah. So if we look at that, we have, if we're going to use So if we want to use the 3 feet, let's see what is happening. From here to here, this is okay. That is a 6. But what else can we use here? Okay, so what else can we use? Yeah.
The one that you wrote at the beginning, saying the 3 feet is from D to E. Can you not get 1.5, the half of 3? Because the half of the length is 6, and the top is 6 feet.
Because what?
The total height of the whole thing is 12, but then since it's cut in half, 6 at the top and 6 at the bottom, can we assume that it's going to be half of 3 as well? Getting the same right angle triangle you drew at first, but this time getting it as 1.5 instead of 3.
Okay. That's,
Or
yeah.
since we're trying to find that angle that is there,
Mhm.
we can just get 12 and 3 to find that angle.
12 and 3. So 12
Yeah.
from here all the way down up to here.
Yes, and 3. And since we're trying to find that angle, we will still get the same angle.
Okay, so we get this and get this. And then this can give us this angle here. Right?
Yeah, but it could also give us, okay, I don't know which angle you're working with, but the angle down can, okay, when you do a Z to give us that angle, that one. I wish I could show you, but yes, that one.
That one. Okay. So you have to see that actually, yeah, the many ways that we can approach this, but this is actually the most straightforward one. But yeah, they all work. So what you have to see here is, as you guys were pointing out, we have this one here, that is 12. And then we have this one here. This is the 3, which is from D to F. So the force we are interested in is a force that is along this line. So we can easily make a right angle triangle here with the right angle being there. Since we know the upper part there, that is a 3, and the height, then the vertical part, this is a 12. So the triangle we have is this. We can easily determine this angle here that can be used to break down the force there. So in other words, the angle that I am going for there is going to be this angle here. I hope you guys have seen that. Yeah, but this was yeah, that was created from you guys. So Mapalo, I want you to try the method that you mentioned of coming up with the 1.5 somewhere there. So I want you to try it as well and see if you get the same angle as we'll find here. Okay, so nice. Okay, great. So let's see how it goes. So from here, you can easily, if I label this angle here as theta, then what are we finding there? We see that tan can work there. Theta will be equals to tan inverse. So we have the opposite is 12. The adjacent is 3. What will be the answer here?
$75.96.
75.96.
It's 9.
Okay, great. So we have found that angle. So that's the angle we're going to use here. So having found the angle, it now means that we can easily get the components. So let's start with the sum of the forces in the y-axis. So we have two forces in the y-axis. We have the 500 pounds itself going downwards. So that is going to be minus 500. Then we have the vertical component of FD. That component to be going upwards. So I can put it here and say it will be going upwards like that. And you have to see that this component will be opposite to that 75. So we use sign for that. So it's going to be sit up, we'll say plus. Its opposite, we use sign. So it will be FD itself, FDE, then sine theta. So they're the only two, so this has to be equals to 0. From here, we're working it out for FD. So the 500 goes to the other side, becomes positive. We end up with FD, DE, that is, being equals to the 500 there, then divided by sine 75.96. What are we getting there?
Five 15.39.
515.39. Okay, don't forget the units there. Okay, so this sorts out one of the forces. Now, the only thing is the member that we are looking at. Is it, yeah?
Isn't it 515.34? 515.4 because it's 515.3966.
Yeah, oh yeah. So this can reduce to just, yeah, we can still write it as that. So this, we can write this as 515.4, or even better, 515 pounds. Okay, so the question now is the member in tension or in compression? What do you guys think?
Compression.
Okay, so what we had was this, and the force that the assumption we made was that it was something like this. So this is to the pin. To the pin, this is what we have, and this holds. But for the member now, what we're seeing is the opposite. So for the member, so first you not say for the pin, there'll be that pin there, and there'll be this pin down here. So for the member, what we are going to expect there is going to be the opposite to that, which is going to be this and this. So these imply compression. Okay, so this is what we expect there, compression. So next up, we now look at in the horizontal axis. FDC is to the left. So we have sum of forces in the x-axis equals to 0. So FDC is to the left, so that is minus. Then we have the x component of FDE. So clearly you can see what is happening there. FDE, that's to the left. Clearly, one of them has to be, must have the wrong direction. And it's only logical that the one with the wrong direction is going to be FDC. You see, it's going to come out. So the x component we're going for is this one here. So it is side by side with the angle. So it will be given by cos. So it will be FDE cos that angle. That was 75.96. So they're the only two again. So this has to be equals to 0. So in the end, we have FDC. This will be equals to minus FDE cos 75.96. We bring in what FDE is. We found 515. So this is cos 75.96. What are we getting here?
That's 125.04.
125.04. So in point. So in the end, this is 125 pounds. What does this imply? Well, it now means that to our setup here, this direction was off, and the correct orientation must have been the alternative. So I can do this and do this. But in most cases, when you're doing these analysis, you guys, you rarely come back to the original diagram and change it. Because if you want to change this, it means that this, when the marker looks at your diagram and sees this minus here and your arrow there is pointing in the other direction, it might be considered to be wrong. So what we're doing for you is, since your assumption was that it was square like this, you maintain it like this. So that your answer remains the way this one is. But if you now wanted to present it as a positive value, it now just means that you have to make a separate diagram to say, okay, now this actually has to point in this direction. Or you can now make, you see, for every calculation I make, I now draw the original member. So when I draw that member, now I'll give it the correct direction. If you look at the way I assumed it here, that it was pointing to the left towards the member. Now, when I draw the member, since I know that direction was wrong, it has to be the other way. I'll say it's like this. This is where the 125 is pointing. So at the other side, I have this as well. So this is towards the pins. So that inside the member, what we're seeing is the opposite. This and this. So we can conclude, in what state is this? Compression or tension?
Compression.
It's compression.
Yeah, so now for this diagram I have made, so you see, I have this one, which is with my wrong assumption. I maintain that minus. But now when I make a conclusion, with my new diagram here, I can conclude that FC, that was CD, FCD is equal to 125 pounds, and it's a compressive force. Okay, so doing this means that you don't have to go back and change signs everywhere else. Because if you change your original diagram here and say that the force there was pointing in that direction, it will imply that in your calculation, you might have to change all this, which might take a bit of time. So just leave it the way it is, make a new diagram here with the right orientation, and then state the force. Okay, so that sorts out the joint at D. Now, where do we go next? So let's go back to the original diagram. I'll remove this. So you have to see that having found what all the forces at point D now gives us something to work with for point C. Point C had three unknowns, this one, and this one, which made it a little bit difficult to work with. But now that we know what this one is, it means that we only have two unknowns, meaning that we can easily work with that joint C. So let's go to the joint at C. Let's see what is happening there. So if we look at the joint C, what is happening there? Well, we have the applied force here, and it's a vertical force, vertical downward force, 500 pounds. Then we have three members. One of the members is already determined, and do you remember the orientation for this member? It was towards the pin. So with that in mind, all we have to do is figure out what is happening to the other two members. So we can make assumptions here. So what assumptions are we going to make? So let's pick CB. So what do you want to do for CB? Do you want towards the pin or away from the pin? You guys choose.
I should be towards the pin.
Okay, towards the pin. So of course you're looking at this this force. It's a downward force. So obviously these two members must be opposing whatever that is doing. So since that is a downward force, you expect these two members to to have a vertical component to oppose that downward force. So that is the guess that you're going to make here. It might not be correct, but that's the logical take here. So you assume this is going like that. How about CE? In what direction? Towards the pin or away from the pin? What do you want to do there? Towards? Okay. So for C, it works as well. Let's see. Above all, if it doesn't, we'll just come back and change them. So you have B here, you have E here, and then we have C here. So you have a 500 on top there. Okay, so let me not cut them. Let me just copy them. Okay, so with that in mind, now what we want to do is get your pin, and right where the pin is, that is where my origin is going to be. Now I want to draw my coordinate axis, or I just want to show the forces acting either horizontal or vertical. So with my x-axis, my y-axis being the vertical, my x the horizontal, let's see where the forces are. So I'll exaggerate this so that the angles can show properly. So we have this, we said this will be the direction for BC. So I can just say this is FBC. The next up, we said here, we'll have this one. And this will be FEC. Then along the horizontal, we'll have, so this was towards the pin. Yeah.
I have a question on joint D.
The D, okay. Joint D.
Yes, when we were looking for DE, what we found for that line, was it DE or it was DF?
When I'm looking for DE, DF, we didn't.
Yes, but when we said that part is 12 and the other part is 3. So doesn't that mean we're looking for the entire line?
No, I get you. I get you. We only used those to find the angle.
Who's there?
You have to see. You have to see that the angle, if I made this small triangle here, with 6 being the vertical, and this, if I made this triangle here, or if I made this triangle from here to there, here to here, and here all the way up to D. You have to see that these two triangles in blue and in red, they have the same angle here. Do you see that, Chewe?
Yes, I see it.
Yeah. So this implies that even though we use the 12 and the 3 there, meaning that we use this hypotenuse, the hypotenuse DF, the angle that we found here can easily be used for the smaller triangle as well. So
okay, I now understand. I think I got confused. We're using those values to find the angle and next day.
yeah, we're using to find the angle. Okay, so we're here. So we're placing down the forces. We have already put down 3 of them. So there's just one more. So for FCD, this is FCD. We said this was pointing towards the pin. So it was in that direction, which is this one here. The last one is the applied force, which is downward. So that is 500 pounds. So how do we work this one out? Well, same thing, sum of the forces. So let's start with the sum of the forces in the y-axis. We can start with the y-axis. So sum of the forces in the y is equals to 0. So for the y-axis, we have the 500 pounds going downwards. So that is a minus there. But then for these two forces, which both have y components, we need angles if we're going to resolve them. So let's go back to the diagram. What angles are we going to use there? So when we come back here, so we can use the same analysis that we made earlier on, but just this side. So in this case, we can take that that sheet that Mapalo gave us to say that the horizontal distance here will just be that the 1.5, or even the same one that we used earlier can still work. What you have to do is, again, from here to there, then to here, then back to here. Okay, giving me something else. Let's say here up to there, then vertically upwards, then horizontal. So we see that here it's 3, here it's 2.6. We can easily get what this angle here is, but you see it's going to be the same math. So you expect that this is still going to be that 75.96. So you still expect this to be 75.96. So meaning we can resolve the force CB using that 75.96. So I hope you guys have seen why I'm saying that that is also going to be 75.96. Okay. So from here, we can break down what this force is. That's FBC. So let's see what is happening to FBC there. So it will have two components. I am in the y-axis, so the y component will be going vertically upwards. We see to say this component will be opposite to that 75.96. So this will be plus FBC, then sine 75.96. Okay, so yeah, let's just revisit that. Okay, that looks okay. Yeah, that looks fine. No. Yeah, this is fine, but this is just a 12. Okay, sine gives us that. Okay, so next up, we need the y component of FEC. So for FEC, we also need to find an angle. So let's find an angle to use there. FEC is here. What angle are we going to use here? Can you guys look at the triangle we're forming for FEC? How are we going to get the triangle here? How will you get the triangle?
So
Yeah.
okay, the way you're doing it is different from the way I'm doing it.
Okay.
I did it.
Yeah,
But
go ahead.
to find, for me, I assumed everything was tension, and then to find that angle, the angle to get CE, using the same thing that Mapalo was saying. I like the length of BE. I found it to be 6.
Mm-hmm.
And then I formed a right angle triangle from C going down, like a straight line going down, which is perpendicular to BE. And that distance from that perpendicular line to E, I assumed it, I found it as 4.5. And then I maintained the 6 feet there.
Okay, so it's saying this distance from C to D, this one here, right?
Yes.
You found it as what?
No, that one is 6.
Yeah.
And then now the length from that line to E, 4.5.
Okay. Okay,
I have a question.
go ahead.
I wanted to ask, what of trying to use the same triangles we formed? That was the triangle, the right angle triangle, the one which had 12 and 6. Is it 6? 12 and 3, sorry.
12 and 3. Yeah.
Yes. Can you just draw it for me? I show you.
Okay. So I draw it about which point?
The
The
original triangle I used to find 75.96.
original, the one on the left side, the one here.
Yes.
Yeah.
Now, since we found angle F, that angle at D,
Yeah.
We know that it's a right angle triangle.
Yes.
So can't we find the angle at F, which will be equal to the angle at E?
The
Is
angle
it the
at
same?
F, which will be equal to the angle at E, this angle here.
Yes. Will it be the same?
I don't think so, unless otherwise. What do you guys think? Will those two angles be the same? They don't seem like they'll be the same. They don't seem like they'll be the same. Yeah, these two might not be the same. Okay, so yeah, this will not really give us what we're looking for. Okay, so yeah, among the things that we can do, we can still use that same approach that Zumila gave us. Yeah.
Is DE and EF equal?
DE and EF, are they equal? I might say they are. They seem like they are, because from here to here, these are the same. And from here to here, that's 6. This is halfway, 1.5. So they just might be. This is the same as this. Yeah, I think they are the same.
So meaning even the other side will have the same values, which
Mhm.
is CB and BA.
Yes. Wait, that's all. I thought there was going to be a follow-up question or something. Okay.
No, just that.
Okay. So yeah, for this part, it's very difficult for us to get something that gives us directly what the angle is, but let's see if we can try. Trying to see if we can find another method that we can use other than the approach that Zumila gave us. But if that doesn't work, then we'll have to stick to what she said. I think what she said seems to be the easier approach. Okay, so if we take the whole thing here to be split into 3 equal sections, so you have to see that this piece and this piece, this part here is a 3. So all we need is perhaps to know this piece here. So again here, you have to go back to what Mapalo said, to say that the distance from here to here, it's 3, halfway brings us to where E is, and that is going to be 1.5. So if you take this as 1.5, then this section here will end up being 1.5. So what you end up seeing here is that this is a 3 and this is a 1.5, so that the distance from this point all the way up to E is going to be 4.5, as Mila was saying. So here we have 4.5. So we now have the 4.5 here, and we have the vertical point from this going all the way up to C as a 6 based on this part. So this implies that we can easily get one of the angles. The angle that we're going to go for in this case is going to be this one here. So you can find that angle. Let me label it as phi. So that angle phi will be equals to, so again, it's working with tan there. It's going to be tan inverse. And this is going to be the opposite, 4.5, over the adjacent, which is 6. What is this angle giving us?
It's like 6.89.
36.87 degrees. So we got this angle. It was 36.87. So let's see how it works there. So we want to get the vertical component of FEC, and that vertical component to be going upward, so say plus. So you have to see that that will be given by cos relative to our angle there. So it will be FEC, then cos 36.87. So that was the last vertical force. This has to be equals to 0. Okay. Any questions there?
I have a question on why you used cos instead of sine. Can you just explain again what you mean when you say it's related to the angle, to the side?
So the idea here is, this is the vector. The angle we found was this one. So when getting the components, we have the horizontal component coming here, the vertical component going up. So when you compare the angle to the side you're looking for, this is the y component. When you compare these two, they are side by side, so it is adjacent. So because it is adjacent, you know to say adjacent works with cos. So in the end, if this is f, you're going to have f in the y, which is here. So you're going to have cos phi is equals to the, you know how cos works, it's adjacent over hypotenuse. So the adjacent is going to be fy, hypotenuse is f. So this is why to find fy, I just said relative, these are side by side, so I'm using cos, the vector itself, then the ratio I identified, the angle I was comparing with.
Just to drag you a bit behind, the 75.96 degrees that we found for joint D,
Okay.
was it not side by side with the angle as well?
The 75, for which component?
The angle for which component? That was DE.
DE.
Yes, for
When I'm dealing with DE, which is, let me see it, yeah, which is this one here. When dealing with DE, to get the X component was side by side here, right? So these two were side by side. So in summing forces in the X-axis, which was here, I used cos. And in the Y-axis, to find the Y component, these are opposite. So I know opposite works with sine. So in summing forces in the Y-axis for FDE, I used sine there. This was when I was summing in the Y-axis.
Oh, okay. Okay, all right.
Yeah.
I see.
Okay, so we're here. Okay, so this is what we had. So you just have to simplify this a little bit. So this is FBC sine 75.96 plus FCE cos 36.87 is equals to 500. Okay, so you can divide, but we'll leave it here. So let's go to the y-axis. What is happening in the y-axis? So in the y-axis, we have, we are coming from the y-axis. We're now going to the x-axis. Is equals to 0. So we have this one here going to the right. And that is side by side with 75. The force is FBC. So we have FBC. Then that is side by side with the angle. So we're looking at cos 75.96. Next up, we have this one here. According to our shape here, it will have a horizontal component and it will be going this side. Horizontal, perhaps let me put it here. Horizontal will mean that it's pointing to the left in this case. And if you compare it to that angle, it is opposite to the angle, so we're using sine. So it's FEC sine. So it's going to the left, we have minus FEC sine the angle, and the angle is 36.87. Then the last force in that axis is FCD. FCD is entirely in the x and to the left, so minus FCD. We simplify this. I'll make FBC subject. Everything else goes to the right side. FCD will become positive. What was FCD? 125. Yeah, FCD was 125, so this becomes 125. Then this goes the other side, it becomes positive, so plus FEC, so this is EC, not EE. Then sine 36.87, then divided by cos 75. So we now get this, plug it into 1. So plug it and simplify. What you get? So yeah, this calculation. Yeah.
I want to know where you got the 2. Is it the 2.399? That number.
The
2.399.
for this one here.
That, yeah.
Yeah, so this is what we got when evaluating which part was that? Yeah, this part. I was distributing the 75 inside the brackets. So the first thing that we did was we multiplied the 125 by sine 75.96, then divided it by cos 75.96. The answer was this one. Next, we multiplied the sine 36.87 by sine 75.96 and divided it by cos 75.96. The answer was 2.399. Is that okay? Is it okay now? Yeah. So when you simplify, we find that FEC is 0. So all you have to do now is find FBC. So we had this expression for FBC. All we have to do is put a 0 where we have FEC. So let me just highlight this one so that we'll come back to it when you need it, when concluding. So now we're just going to put a 0 there. Our expression remains or becomes 125 over cos 75.96. What will this give us?
That's 515.25.
515.25 or
5.39.
yeah, 0.39. Okay, in the end, this is 515 pounds. So this is what we have. And what can you conclude? The member BC, compression or tension, it's here. Our assumption was that's BC. Our assumption for BC was that it was the force was going towards the pin. So compression or tension. Okay. So that is going to be compression. So I can sketch it for you, but I think you guys get how it goes. So this is compression. Okay, so we now have BC. We also have EC. So we're only left with a few more. Okay, so let's try to pick up the pace. We're now going to go to joint E. What is happening to joint E? The joint E, where is it? So if we come back to our structure here, E is here. We know what this is. We know what this is. We only do not know this. We do not know this. B was a little bit, yeah, we could have worked with B as well, since we know this, but we don't know this. That's the problem with B. We don't know that. We don't know this. We also don't know this. So we would have had 3 unknowns. So B would have been tricky. So instead, we choose E. For E, at least we have 2. The only things we do not know are the other 2. So I can easily work with them. So again, like before, first let's see what we know. From what we know, here we have nothing. That's a 0. So we can as well blind this one out. So I want to look at this one. It won't affect what we're doing here. Then with that in mind, what else are we saying? DE. For DE, what did we find? Towards the pin or away from the pin? DE was away from the pin. Was it? No, towards the pin. That was towards the pin. Okay, I don't have that diagram there. So DE was towards the pins. So because of that, here, we know this is towards the pin. The next, we have a horizontal one here. We make an assumption. Where is it going to go? Then also EF. EF will be easy to predict because you already see what is happening on top. If DE is coming towards E, then your prediction is that FE has to also go towards the pin to oppose what the other one is doing. Now, I want to teach you guys one trick here. If this is the case and you actually observe that this CE is not doing anything, CE is not there. If you have a structure where you have members like this, the 3 members, I'm not considering CE here. You have 3 members, DE, EF, and EB. I want you guys to make a prediction for what the force through EB is going to be, just by observation. What do you think this is going to be? Can we use observation there? Is it possible for us to find what this member is going to be, what the force in that member is going to be, just by observation? Okay, so what I'm saying is this. Whenever you see structures where you have, okay, let me bring one more diagram there so that you guys can actually relate to. So we're going to use this one to just tell you guys exactly what I want you guys to get here. Whenever you see a joint where you have 3 members, this is in equilibrium. This joint, you have a force along this member, and you have a force along this member. See, by observation, you should actually be able to predict what the force in the third member is going to be. See, what happens here is the 2 members will oppose each other. You can actually look at it as if this member here, the line CE here, you can look at this as if it was one of the coordinate axes. So picture this CE as your x-axis. If you pictured CE as your x-axis, look at what happens. If CE is your x-axis, then you expect that the members DE will be equal to the member C, that's DC. These two will have to be the same. If these two are the same, then whatever is happening here, you can actually predict what it is. Can you make the prediction?
0.
0. It will have 2 components. Yes, you can break the components up, but the fact is it won't be affected by this because it's being cancelled by this. In the end, this is not interacting with anything, so that has to be nothing. You can make the same prediction even when you look at this one here. The whole thing starts with the system being in equilibrium. You can easily pick this line to be the coordinate axis, the x-axis. If that line is the x-axis, notice that you can argue to say that for this joint, the components will be the x component that will be through this member will be going this side, and through this member, it will be going this side. These two, since you say sum of forces in the x has to be equals to 0, these two have to cancel each other out. The only one left will be this one. Regardless of how you look at it, that one will be interacting with nothing. So in the end, it's only logical that its force or the force to that member will have to be 0. So because of that, this one here, the force to this member will have to be 0 there. But you can't do the same thing here. You can't do the same thing there. Why am I saying that? Because in as much as you can make the same analysis for this member and for this member, you have to see that this one here will interact with the applied force there, such that it will have to oppose the applied force in that way. So it won't be equals to 0, it will oppose the applied force at that point. What am I trying to say when it comes to our question there? If we go back to our question here, when you look at this joint at E, we already saw that CE was 0 there. So through calculations, we saw that CE was 0. If CE is 0, then we can look at this diagram as if CE was not even there. So that now this looks like those joints were just from analyzing. If that's the case, and this joint is in equilibrium, you have to see that DE will be opposed by FE. If you were to select this as your coordinate axis, you can even say that sum of forces along this coordinate axis is equals to 0, so that this and this will cancel each other out. What remains will be this member, and this member will be interacting with nothing, so that in the end, the force along this member has to be equal to 0. Knowing a technique like this will be very helpful in saving you a lot of time, because just by inspection here, we have concluded two things. One, that the force along that member, let me erase this. Okay, so through inspection, we have made two important observations. The first one is that whenever you have a straight line like this and you only have three members interacting like this, choose the straight line. It has to be a straight line. Choose the straight line to be a coordinate axis. If you did that, then it would imply that the forces along these two members must be equal, but opposite, of course. So this implies that FDE has to be equal to FEF. They just have to be opposite. So what did we see for DE? DE was going in what direction? Where's DE? DE was going towards the pin. So DE was towards the pin. This implies that even FE has to be towards the pin. Same direction, as an opposite direction, same magnitude. So that is our conclusion for EF. So what was the magnitude for DE? DE was found to be 515. So even EF also has to be 515. EF has to be 515 as well. But is it compression? Is it tension? So what we're saying is it has to be towards the pin. So let's do that. Towards the pin. So we're seeing this, seeing that. So the internal forces, we're seeing something like this. This is compression. Do you see that? See, the same observation could have been made for the most recent assignment that you had. In the assignment, you had this structure here. It was something that was a little bit, it was very, very long, but you observed that you could have applied the same concept at the joint at D here. By observation here, you should see that this again has three members. Two of the members are connected along a straight line. So if you chose this to be at a coordinate axis, notice that you could have easily said that at this joint, you have a force, let's say, towards this direction along this member, a force towards this direction along that member, meaning that these two will be equal but opposite. They'll cancel each other out, leaving this member all on its own, unopposed, implying that this member, the force in it, has to be equal to 0. Even if, let's say, the other two were towards the pin in a way, you should see that even if that was the case, okay, I don't want to do that, okay. Even if that was the case, you still come back to the same conclusion. If this unit is going like this, and this one is going like this, still these would oppose. They are equal but opposite. They oppose each other, implying that this would be unopposed and equals to 0. And you guys remember, we did this calculation, or should I say you did this calculation, and you found that the force along this member was 0. So you calculated and you found it was equals to 0. Now what I'm showing is you could have just observed the setup and concluded that it's equals to 0. Okay, so I hope that was helpful. I hope it's something that is going to save you a lot of time when you're dealing with such structures. So just trying to show you to say it actually holds.
So,
Yeah,
a question.
go ahead.
So if such a question was to such a question, you do give a statement for you giving it a zero member, something like that. It can be calculated.
You can. What you do is look at how much time you have. You want to look at how much time you have. If it's a question that has a lot of marks and it doesn't involve too much, like, yeah, it doesn't involve too much, and then you have enough time, of course, you want to calculate and show mathematically that this is equals to 0. But look at the way this question was. This question was using the method of joints, determine all the 0 members in this truss, and assume all joints are pins. So the way this one was, you can still use calculations to show mathematically that these are zeros. But for some of them, like the same ones where I'm saying you can just use observation, and which you really don't have time, like in a test and an exam, you really want to save yourself some trouble. You can make conclusions to say this is 0, this is a 0, without going through the math. Because knowing that this is going to be a 0 member and this is also going to be a 0 will save you a lot of time in determining what is happening elsewhere. So, of course, for this question, there might still be other members where the forces are 0. So first, eliminate the obvious or state the obvious, then go elsewhere and make calculation to find that just in case, maybe this is also a 0 member. Maybe this is also maybe it also has 0 somewhere there. So just put a math everything else that requires you to do math. But for something where you can save time, you really want to save time, unless if you've got enough time. Have you got that?
Yes.
Yeah. Okay, any other questions before we proceed? Okay, so our quick analysis there gave us two things for joint E. First, it led us to a conclusion that the force along that member FEB, that force there was equals to 0. And apart from that, it also taught us one thing. The force along the member EF is going to be equal to 515 pounds. And the conclusion there was that that was in compression. So next up, we look at the joint at B. For the joint at B, what is happening? Well, the joint at B is here. So for the joint at B, again, we quickly see one thing here. Can you guys make a conclusion here? Can you use the technique that I've just showed you to make a conclusion there?
So FBA is equals to FBC.
FBA is equals to FBC. Yes. So that's the first observation. FBA is equals to FBC. And for FBC, remember FBC we said was, if this was the member there, FBC we said it had forces like this. So it is towards the pin. So if this is our pin, FBC is towards the pin, then our force has to be towards the pin as well, to oppose this one. So it has to be towards the pin. So since that is the direction of our force, then what we have is something like this. Then the other force is something like this. So our force FBA, compression or tension,
Compression.
okay, so our force FBA has to be compression. Okay, so FBC, remember, was 515. So this has to be 515 pounds, and this has to be compression. Then what other observations can we make here? So by observation, we've sorted out this. What else can we conclude here?
FB is equal to 0.
FB what?
BF.
FBF is equals to 0, yes. So again, what you're seeing here is, since we have found this member to have a force of 0, then this is what we now have. Again, 3 members only, 2 of them along a straight line. So they have to be equal and opposite, implying that the third force has to be O on its own. So BF, that member, must be O on its own and equals to 0. So FBF has to be equals to 0. So FBF has to be equals to 0. Okay, so that sorts out that joint. Any questions there?
Just quickly explain how you saw that is it FBA was in compression?
Okay, FBA was in compression. So FBA, the first thing was when we got this, the joint was, let's say we had that. So we had something like this. The joint was somewhere here. So the first thing that we did was to look at this one. It's this one that helped us to predict what was happening here. So for the member on top, that was, what was the label there? Yeah, that was CB. So we had C here, we had B here. For CB, remember our assumption was that one force was going up. Our assumption, which turned out to be correct, one force was going up and the other force was going down. That was for CB. So because of that, so let me just get CB. Okay, that won't do it. Okay, so this was CB here. Okay, remove it from this side. So that was CB. So this is what we had. So because of that, we know to say that since the forces for the new member here, which is BA, for BA, it has to be equal but opposite. So when you pick, for example, at this joint, BA has to oppose what CB was doing. CB was pushing the joint here. So it means that BA has to push the joint in the other direction. So BA had to push the joint upward. So the forces from BA, one had to go like that, and the other had to go down like this. So since these are now the forces acting on the member BA, now what state is it in? We know to say if that is what it is doing to the joints, then inside what is happening is that you have one coming like this, and you have one going like that. So inside, we're seeing compression. Have you got that?
Yes.
Okay. So in doing this, I think we've accounted for all the members, have we? I think we have. Okay, so I think we have accounted for all the members present there. That's everything there. Any questions before we conclude?
Sir,
Yeah.
since it's like everything is almost the same, is it safe to assume that like, okay, if we're trying to find the reaction forces at A and F,
At
is
A
it
and
okay to say, yes, is it okay to say that in the X, for both AX and FX, it's 0, and then in the Y, it's 500?
in the Y, it's 500. Okay, so determine the force in each member trusted to member. Oh, okay. So you're saying if we wanted to find the reaction forces, is it safe to say that in the X it is 0 and in the Y it is 500? I think, yeah, in the X it is 0, yes. In the Y, is it 500? In the Y, is it really 500? Okay, so what you have to see here is if you wanted to find what the forces are, the reaction forces, you forget the internal forces. You can look at it now using only the external forces. So of course you have the horizontal forces. So I can say this and this. And then you can say this and this. So you start by, you can use rotations here. You can use rotation. The sum of the forces here will tell you to say that the x components have to be equal but opposite. So the forces in the x have to be equal but opposite. And then when it comes to sum of the forces, if this is AY and this is let's say FY, this would tell you that AY plus FY has to be equals to 1000. Yeah, in the end, I think each one of them will likely end up being, might not even be 500. Let's try to see. So once you get this expression, you can now go to the moments, sum of the moments. So some of the moments, you can start with some of the moments about A. If you do the moments about A, it means that this will not cause rotation, this will not cause rotation, this will not cause rotation. Only these will cause rotation, these three. This will allow you to get what Fy is. Fy will be causing anti-clockwise, so it will be Fy times the distance, which is from here to here. That distance is a 9. It's going to be 9 Fy equal to, the other two be causing anti-clockwise. This, the distance is 3. So it's going to be 3 by 500. The other one, it's going to be this by 6. So it's going to be plus 6 by 500. So in the end, Fy will be equals to 3 by 500 plus 6 by 500 over 9. What is this giving you? What are you getting here?
Good.
500. Nice. Okay. So looks like they are 500 because of course you are going to get the same value for the other one. So if this is a 500, then you expect the other one to also be a 500. Okay. So any other questions, you guys? Okay, so this was a long session. I hope it was helpful. Would you guys want us to still do more questions on joints, or it's okay, we can move on to sections tomorrow and conclude trusses in 2D at least?
We can move on.
Okay. What others say?
Yeah.
Okay. No, great. So tomorrow we're going to look at, we can look at sections tomorrow. So yeah, if you guys have any questions that you might want us to look at, please feel free to forward them. We'll see you guys tomorrow morning. Oh, we also have maths tonight. Bye guys, enjoy your day.